Okay, so kinetics, which is the new topic we're starting today, is going to feel very similar to physics for a couple of minutes. And I see all of you are like, yeah, I love physics. That's the best ever, especially Andrew. In the velocity part of physics, like meters per second, and acceleration, and time, and distance. But there will be no distance. We're not going to be like, how far can we throw an argon atom or something like that, if it's traveling at this speed and acceleration and stuff. No, it's going to be how fast does a reaction move. What do we usually measure for how much stuff is in a reaction? What are the units we usually are working in? We measure how much stuff is there. Moles. And if it's in a huge volume, we might say molarity, moles per liter, right? Well, we're going to be measuring how many moles per liter are there as a function of change in time. So it's moles per liter versus time. Versus in physics, you might measure the change in distance over the change in time. Right? So this is a rate. It's the change in concentration. Whoa, already doing funny things in the video. Great. It's the change in concentration, which is usually referred to as molarity. For the most part, the volume will not be changing. And if the volume is not changing, it's really, you could look at it as the change in moles per time. But to actually do that, you would have to multiply the molarity times the volume. If it's the change in moles per time, what could you also change the moles into? Grams. And those conversions would all be proportional as long as it was the same substance. So the change in grams per time would be proportional to the change in moles per time, which would be proportional to the change in molarity per time. We tend to work only in molarity, except with half-life, we'll do mass. We are going to work with natural logs today. You don't actually have to necessarily know how to use the natural log, but you need to know how to push buttons on a calculator and to do the opposite. What is the opposite of the natural log? E to the, right. You're going to exponentiate it. So if you're taking the natural log of 2 is equal to x, you could take the e of both sides and say e to the 2 is equal to x. You could solve. I think I said that correctly. So in our first kind of data here, this is the data of, and I'm really talking loud into the microphone, so I apologize. You might need to turn down your volume. This is the data set that might be arrived for a reaction between hydrogen and oxygen. What do we have? 0.05, 0.08, and 0. Let me just insert a blank page and kind of make a graph here real quick. So we have a graph. This is concentration. This is time. 0.05, 0.10. What is the starting concentration in your data for hydrogen? 0.05. So blue is going to represent hydrogen. What is it the next point, and how much time? 0.025? And at 0.002 seconds? Is the next time unit 0.004 seconds? All right, so they are proportional. So each of these time values is a difference of, 0.002. And you'd have to make sure that each time value was the same apart, right? Your x-axis, each value on the x-axis has to be the same distance apart. If that data didn't go in perfect intervals, your graph would still have to go in perfect intervals. You can't just go, I'm going to plot random points on the... You have to actually divide the x and the y-axis up in equal bits and pieces. What is it at 0.004? Say... All right, having some... Hydrogen starts at 0.05, and then it's at 0.025. Ew. Why does that not start at 0? That's horrible. Shift all the times down. Start with 0. All right. It should have been initial time 0. I need to fix that. No, we're just going to shift the time down. The data's wrong. At 0, it's 0.05. And then shift all the times down, all right? So at 0, it's 0.05. At 0.02 seconds, it's 0.025. So all that data needs to be shifted. My fault. And then it kind of makes that curve, right? This kind of slow decreasing curve like this is a natural log curve. If we did the natural log of this versus the time, it would be a linear curve. It would actually be a straight line. What is going on with the oxygen? It's starting off at like 0.08 at time 0, and then 0.65. And this is all estimated here. This is kind of be ugly. 0.64, 0.612. Is oxygen quite as steep? It's not as steep, is it? What does water start off as? 0, it's a product, and then it slowly increases. It actually hits right there also, 0.025, and then there we go. Water's also in red. So this one is water, this one is oxygen, and the blue one is hydrogen. But this is not perfectly drawn graph. If it was, I could have used Excel to make the same graph, but you can definitely tell that the slope of oxygen and hydrogen are not the same. And their slopes are directly related to the reaction. The slope of hydrogen is twice the slope that of oxygen. Why do you suppose? Yeah, you lose 2 hydrogens for every 1 oxygen you lose. You lose 2 of these for every 1 of these. So the rate or the concentration of hydrogen is decreasing at twice the pace. And then what do you suppose the rate of water is equal to but opposite of? Water's formation. It's the equivalent rate of hydrogen. They're both a 2-to-2 ratio. So for every 2 hydrogens we lose, we make 2 waters. So look how they crossed, right? They crossed, and I didn't draw it perfectly, but this, if you took the inverse of this, would probably be that, wouldn't it? It's not perfect, but it's my attempt at perfection. And then we have in our notes here, we have that written as this, that like if you had the oxygen's change in concentration and multiplied it by 2, it would be equal to hydrogen. So if you multiplied hydrogen's rate change times 2, it would equal to oxygen's. We've talked about how brackets mean molarity again, but let's just mention it. If it's in brackets, it technically means molarity. It's okay if you leave it as moles per liter. All right, I have a really bad graph of that right there, which I just erased. And then kind of that same explanation. How would you figure out the rate of something if you were actually doing a lab in physics? You might measure one point it was at and then how much time it took to get to the next point. Okay, it traveled 4 meters, it took 2 seconds. 4 meters in 2 seconds, that's 2 meters per second. You pick 2 points and you measure them. And you compare the time versus the distance. Or strike that, reverse it. In this case, we're going to compare the molarities at 2 points versus the time at 2 points. And you compare the difference and you can get the rate at those 2 points, the rate of change. And if the oxygen is truly half the hydrogen, if you know the rate of hydrogen, you could divide that by 2 and you know the rate of oxygen. They should be directly related to each other. What's nice about the rates and the data is you can look at it and test it really easily. This is really going to be a data-driven topic with graphs and discussions about labs and things. And you can look at the data, and if you understand the material, you work your way through the right answer, and then you can immediately test the answer to make sure you did it right. which is unlike most of the other chapters. A lot of times we're like, here's the molarity and the mass, and I think this is the answer, but I don't have a clue if I really did it right, because you all know that you're going to make little mistakes. But in this chapter, when you get to the answer, you can immediately take the answer and plug it back into the data and go, yeah, I did it right. And that's one thing that's kind of nice about this chapter. Here's a hypothetical reaction where we don't know the coefficients, but we do know the rates. We do know the rates. And figuring out the concentrations and the rate changes can be tricky in an actual lab setting. You have to have the right sensors, the right equipment, like pH probes. Maybe the pH is changing. You'd watch the pH change, or maybe you're making a gas and you're collecting it. You can measure the collection of gas over time. In fact, at the Chemistry Olympiad last week, or 2 weeks ago now, have I talked to you guys about the Chemistry Olympiad ever? Pause. So the lab they just did the other day went like this. You have 6 molar hydrochloric acid and a eudiometer. And a eudiometer looks like a really long test tube. Oop, that's not a pencil. It's a really long test tube. It's usually not wobbly like that. And it's graduated, though. And 0 was up here, and maybe this was 5, 10, etc. And they filled this eudiometer with 6 molar hydrochloric acid. All right? 6 molar hydrochloric acid, and it's in a beaker that has some water in it, so the hydrochloric acid can't get out. And then they put a piece of zinc down in here. Let's change the color to red just for fun. So you have a piece of zinc, and the zinc and the hydrochloric acid are going to react and make hydrogen gas. And their job was to collect data as to how many milliliters were produced per second. Does that make sense? So at 10 seconds they had 5 milliliters, and at 10 milliliters was at 17 seconds, and then what's the next? Probably 15 was at 23 seconds, and then they could graph volume versus time. Then they were asked further questions, like what would happen if you changed the molarity? Not the amount of zinc, but if I change this molarity from 6 to 12, what do you think would happen to the speed of the reaction? Yeah, you would think maybe twice as fast. It actually goes 4 times faster for reasons we'll discuss today. Because that has a squared impact. Yeah, it has a squared impact. Changing the molarity for this reaction has a squared impact, and they could collect data. Now, they only did the 6 molar versus zinc, and they get great data, and it goes really fast. If they had done 3 molar, it would have gone slower, right? Because there'd be less collisions with the zinc per second, and therefore fewer reactions per second. Does it appear to slow down? Yeah, it does, because you're going, it took 10 seconds to get 5. If it was the same rate the entire time, this would have been, right? Actually, it looks, I think I made it speed up, didn't I? Oops, I didn't mean for that to happen. Let me change my data, which is not something you're ever supposed to do. Sorry, if this took 10 seconds, the reaction should slow down as you're using up hydrochloric acid. And so maybe this takes another 12 seconds. So this would be at 22 seconds in. And then 12 plus maybe another 2. So maybe at 30, let's say call 35 seconds. So it is slowly decreasing in speed. I didn't think about that when I was writing it up there. And so they could even create a graph of volume versus time and the rate of volume change. This would be the change in volume versus time, and it would have been a natural log graph also. You would have been, as it decreased, as the reaction rate decreased. Look at this one. We have 4 different rates for 4 different components, A, B, C, D. And we're supposed to try to kind of guesstimate the coefficients, because rates are generally related to the coefficients, not always exactly related, as we'll discuss, but generally related. Look at A versus D. Which rate is faster? A? It's 2 times faster, isn't it? Is D the slowest of all of those? So that's the good one to start with. What's the relationship between D and C? Wait, yes, Courtney. It's has a reaction speed of 0.025 versus 0.075. 0.075 is how many times faster? 3 times faster, right? So, and this one is 2 times faster. And with some fancy math, we would see this one is 6 times faster than D, if you relate them all to D. So you might hypothesize that the coefficients, I don't know why I already have the 2 here, I shouldn't have, were 2, 6, 3, and 1. That might be the case. There might be another step in the reaction that's speeding it up or slowing it down, and we're going to discuss multi-step reactions today. But it looks like A is twice as fast, so its coefficient should be twice the coefficient of D, at least in whatever's determining the speed of this reaction. The other thing is some of these things are actually decreasing. These should actually both be negative, right? A and B should be negative rates because we're losing A and B. Why are we losing A and B? As they make C and D, they're reacting. We are going to only, this is a good thing in this chapter, every one of these reactions in this chapter is going to say, you have reactants and no product. All right? So if you have no product, can the reaction go in reverse? No, it can only go forward. And so the forward reaction, you'll be losing reactants. You'll be having to make, great English, and it's recorded, awesome. You will definitely be producing products. So the product production will always be positive. The reaction production will always be negative. And there's math backing up that logic. So we'll be studying the rate and the concentration as it's implied, as it's related to rate. We will only have reactants. We will not have products. That's what's going on in question 1. The rate law. A rate law is an expression, a mathematical expression that shows a relationship between rate and concentration. And later on we'll talk about how it is also related to equilibrium constants, which we've already learned. But rate, here's the generic expression, rate is equal to K, concentration of X to some power. And we will test what impact concentration has. We already discussed the hydrochloric acid scenario. What did you say would happen if we went from 6 molar hydrochloric to 12 molar hydrochloric? Faster? Faster? So if you increase the concentration, the rate increases. So what we could figure out is if I doubled the concentration, does the rate double? If I double it, does it quadruple? If I double it, does it increase by a factor of 9? If I double it, does the rate not change at all? Sometimes that's the case. Sometimes the rate won't change if you double or cut something in half. And so we'll do that based off of hard data. We'll look at actual data, and the data has rigged numbers so that it comes out nicely. When you guys do your lab on Friday, it's a real lab, and so you'll might get like a, double this. That should be 4 times faster, but you got 3.9. Man, that's close to 4. Good job. It's hard to measure in the real world. K is a constant that just relates the two together so that they be equal to each other. We'll be solving for that. N is the order. And we're just going to go right into some math to kind of explain what these things mean. We'll also be talking about integrated rate laws as if someone took the integral of that. How many of you guys have taken calculus or in calculus? Is anyone here glad they're not in calculus? Okay. So we're not actually going to take integrals. Someone has already integrated it for us. Yay. But it works really well. it's really easy to use. Let's go ahead and jump to some data. Let me remove all of those lines. So here's some real data that I took and plotted. It's the concentration versus the time. And if I did the slope between 2 points, I would have the rate of change. So if I did the slope between these 2 points here, I would have the rate of change. If you change the molarity, what happens to the rate? If I increase the molarity, what would happen to the rate? It would increase. But so here's the molarity at 1. If the molarity was 2, that slope would be a lot steeper. If the molarity was 0.5, that slope would be a lot less steep. And eventually, if the slope reached 0, what would be the slope if it started at 0? 0. There would be no reaction rate. Without any reactant, you have no rate. Also, I'd like to point out, what does it look like is slowly happening to this line? It's getting closer and closer to 0. And eventually it will flatline. And once it flatlines, that reaction has reached equilibrium. It's no longer moving with any reasonable pace forward. Did you have a question? No. Yeah, you had your hand up, and then are you just stretching your fingers? That's allowed. Again, we're only going to ever start with the reactants. There will be no products get in the way. Time for some real data. Let me zoom in here. So, here's real data. And the idea, and you might want to just jot this down. There's 3 trials. Add that over here. Trial 1, trial 2, trial 3. All right? So here's the idea. John is doing trial 1. He has been given 0.35 molar A, whatever A is. And Joseph is doing trial 2. He's got 0.70. And then Dara's got trial 3. She's doing 1.05. And they're all measuring the initial reaction rate. So John puts A into the test tube and starts a stopwatch and stops it the second the products are visible to some point. Joseph does the same thing. Dara does the same thing. And because they have different concentrations, the speeds are different. Which of these is the fastest in speed? Which one has the fastest rate? Trial 3. And yeah, the first one's evil because it's 10 to the minus 4th. I would convert them all to 10 to the minus 4th so that they're easier to compare. This would be 29 times 10 to the minus 4th, 64.5 times 10 to the minus 4th. I just move the decimal over so they're all times 10 to the minus 4th. Then they're easier to look at. Plus, if they're all 10 to the minus 4th, you can ignore the 10 to the minus 4th to compare them. So we can see that Dara, who has the highest concentration, also has the fastest reaction rate. So that implies increasing the concentration of A increases the speed. That is not always the case. You do have to look at the data and figure it out. Now we're going to take it a step further. We're going to try to figure out what is the impact. So if you compare these two, what has happened to the concentration? Compare trial 1 to trial 2, the concentration has been increased by a factor of 2. It's 2 times greater. So they've doubled the concentration. Now let's compare these two guys. They went from 7.2 moles per liter second to 29 moles per liter second. I'm ignoring the 10 to the negative 4th because it just makes the math easier. Well, this was easy. You could do probably 70 divided by 35 and get 2 in your head. Here it's a little bit harder. 29 over 7.2. Elvis, I saw your fingers. How many were there? 4. Yeah. That's 4 times greater. As we doubled it, it is now 4 times greater. What the heck does that mean? Let's take it a step further. Let's compare John and Dara's data. So as you go from John to Dara, what's happened to the molarity? How many times greater is Dara's than John? 3 times greater. So let's compare 64.5 to 7.2. 64.5 to 7.2 is how many fingers? Yes, or 9. Yeah, that was 8.95, and the data is never going to be super duper perfect, but that is darn tootin' close. Yeah, I said tootin' to 9, right? So they tripled the molarity, and the reaction speed for this one and that one is 9 times greater. What is the relationship between changing A and changing the rate? Can you infer what the relationship is? It's a squared impact. The rate changes in a squared relationship to A. As A changes, the rate changes, but not proportional at a squared impact. So, and all that is kind of worked out below. I actually typed up all that reasoning that I'm saying here. So could we solve for K? Could we solve for the rate constant? This is what I meant by this is an awesome chapter. You'll know whether or not you did it right or wrong. Pick a trial, 1, 2, or 3. Who do you like better, Laura? Joseph, John, or Dara? Of course you do. Why are you going to like Joseph or John over Dara? She's awesome. And so you pick Dara's trial and you throw it in there. You have the concentration, square it. You have the rate, put it in there. Solve for K. You now know K. If you're not sure whether or not you did that right, you take Joseph's data or John's data and throw it in with that K. You take Joseph was 0.70 squared. You just figured out K. Multiply it by K. That should equal this rate, shouldn't it? That's one beautiful thing about this chapter is once you solve a problem, you can then immediately test to see whether you did it right or wrong, assuming you're willing to realize that this data is not 100% perfect. It's lab data. It's fake lab data. It's close to real. So if you had, you plug all Joseph's data back in and you get 2.87 times 10 to the minus third, you should do a happy dance. So if you plug the data back in here and you got a 2.87 instead of 2.90, that's fantastic. All right? So it's immediately testable, and that's really nice. So I did that, except in question 3 here, I tried a hypothetical, what if Elvis tried 0.16 molar instead? He knows K because we figured it out using Dara's data, Joseph's or John's. It wouldn't matter. We'd get the same one because K stands for constant. Yeah, I could read your lips, Laura. Not Laura, Paula. Sorry. My bad. Both end in Lara. So I plugged in Elvis's 0.16 for A. I used K. And somehow my -4 disappeared there. And so I'd get the rate. And again, it's slower. And what's beautiful is it works pretty well. Works pretty well for fast reactions. If the reaction's not too fast, if the reaction's too fast, how could you solve for K? Let's say Mark is doing a lab and he immediately realizes this reaction is too fast. How does he figure out the rate expression, the rate reaction? Slow it down. How do you slow it down? Say again. Cool it. Okay, well, you change the temperature, you change everything. All right? So we're going to do it at the same temperature, change the concentration, change the moles. Yeah, you guys are kind of on the same track. If Mark put way less in, if he was at 1 molar and it was way too fast for him to measure, he goes down to 1,000th of a mole per liter. The reaction slows down. Now he can measure the rate. Then he doubles it. He can still measure the rate. He triples it. He can still measure the rate. Now he can't measure the rate, but he's got enough data to figure out what K is, and then he can just, well, here's why I couldn't do it at 1 molar. The rate is 1 billion molecules per second. Moles per second. More data. Ooh, let's erase all of the work and do it ourselves. So in this scenario, there's two components that have to collide to make the product. Components are A and B. One of these might have a direct impact. Do I double A, the rate doubles, or I double B and the rate doubles. One might have a squared impact. I double B and the reaction rate is now quadrupled. I double A, the reaction rate is quadrupled. One might have a zero impact. What would that mean? I double B and it has zero impact on the rate. What happens to the rate? Stays the same. That's kind of a nice one every once in a while. You're like, oh, they doubled B here and the rate is the same number. They double, it's the same. Oh, okay. It's to the zero power. Those actually simplify the problem. Because if you get something that's to the zero power, and this is not, but say this was to the zero power, then all of this data could be scratched out, and it really simplifies the problem down. All right, let's look at this one. Do you want to start, Andrew, do you want to start with A or B? B? A. A. All right. So we have to find a point at which A is changing, but B is not. Find two reactions where A is changing, but B is not. 1 and 3. Yep, because he said 1 and 3. I'm not sure whose voice that was. Might have been Mark's. Yeah. So B is not changing. See, B is not changing. So if it's not changing, the rate is, though, isn't it? Is the rate changing? But B isn't. So B can't be impacting the rate right now because they didn't change it. All of that change in rate is due to what they did to A. What did they do to A? They doubled it, didn't they? What happened to the rate? How much faster is the rate for reactions 1 and 3? It is just about 4 times faster. Just about 4 times faster. So what is that hint is occurring with A? Hints that A is squared, right? Has a squared impact on the rate. That's what it hints at. Could we test it? Could we find another spot? Turns out we can't. There's not another spot with A to kind of test it, is there? But we'll be able to test it at the end when we find a K and all that stuff and plug it into a random trial. Now let's do B. Which reactions could we pick for B? 2 and 1? Yeah, that would work. 2 and 1 would work. You could also pick 2 and 4. That's not going to be as easy to do, though, because it's not a straight up doubling. It's like a 0.5 or 1.5. I would definitely go with 2 and 1. With 2 and 1, it is 3 times faster, right? I mean, not 3 times faster. 3 times the molarity. What's happening with the rates of 2 and 1? It's also 3 times faster. So we tripled the molarity and we got triple the speed. We could have also picked 1 and 4, couldn't we? 1 and 4 wouldn't have been bad. Let's try that. 1 and 4. What happened there? It's times 2. 1 and 4. It's times 2. That definitely implies that B is to the first, doesn't it? That as we double B, the rate doubles. As we triple B, the rate triples. And so right now we would have rate is equal to K A squared B to the first. And they refer to these as orders. So A is to the second order, B is to the first order. I forget to use that terminology. I will ask questions, though. I'll say, what's the order with respect to A? So what's the order of the reaction with respect to just A? 2. What's the order with respect to B? 1. The overall, what's 2 plus 1? So the overall order is 3. It's a third order reaction. How would you solve for K? Courtney, yeah. Good. Thanks for raising your hand, Courtney. at any one of these points. Yeah, so maybe you pick, which one have we not used at all? 5. So we pick 5. We plug 0.3 in, square it, plug 0.6 in to the first. We don't know k, but we have a rate, so we could solve for k. And then we could test that k against one of the other 4 and feel good about our data, right? That's one thing that's really nice. So everything I just said is on this page, really thoroughly worked out with math and stuff, all right? Like, oh, look, if you divide these two, it's a 3. And divide those two, it's a 3. Yay! And so 3 is equal to 3 to what power? 1. And then I did the other one. Here's A. Same idea. You get the square. If you're watching a video, pause to read. Then we could solve for K, like you just said. We could plug in values and get K. It works really well as long as the data is good data. When we do our lab, our data is going to be good for some of you and for other people. I'm not saying who I'm pointing at on video, but I am pointing at somebody. It's not going to be great data. No, it wasn't that bad last time. All right, number 4. You guys, I'm going to actually pause the video while you guys look at number 4 and pick some spots, all right? We're going to pick a spot. Where should we attack for C? Where should we attack for D? Where should we attack for E? So we picked 1 and 5 because D and E weren't changing for C. We picked 2 and 3 for D because C and E weren't changing. And then for E, we're not happy with what we had to pick, but it's the only choice that works right now. And so we're just going to go in alphabetical order. You could do it in any order you want. So with C, we have 4 times. This concentration's been 4 times. And I want to make sure we understand. Reaction 1 has 4 times what reaction 5 has. Right? So I'm actually going to maybe even make an arrow. So this is 4 times greater. So how many times greater is rate 1 when compared to rate 5? No, you're right, it's 2. It's 2 times greater. The speed is double. But the concentration is 4 times greater, isn't it? So that's going to be hard to work out. You got remember the rate is 2 times greater versus C to what power? And C was changed by a factor of 4. 2 is equal to 4 to what power? 1/2? 0.5? That's not a nice number, is it? I'm not really going to do that to you in the future, but you might not have a whole number in the real world. If you're really doing a real lab, you could have a fraction for the order. And that's just ugly looking, though, in the math. But so the rate, this is the rate. Because remember, its rate is equal to kx. We quadrupled it. So I plug, and then x to the n. We quadrupled x. The rate did only times 2. So n has to be the 1/2. And that's not pretty. Let's go to D. I think we're going to like D. All right? What'd you say? 0. Why is it 0? Yeah, look. They changed the molarity, but the rate is the same. So that one's easy. 0. We just figured that was to the half. That's 0 because if you're changing something and there's no change in the speed of the reaction, then that component must not be impacting the reaction too much. However, and here's where I'm going to analogy land for a minute. These 3 ladies have a temporary job. They're going to make pizzas for the evening. And your job is to unwrap the pizza. Your job is to put the toppings on. And her job is to throw it in the oven and pull it out. Okay? Which of these 3 steps is probably the slowest step? Unwrapping pizza, putting on toppings, or putting it in and out of the oven? Probably in and out of the oven, right? If it takes you longer to unwrap a pizza than it does for her to cook the entire pizza, right? So which of these steps is going to determine how many pizzas you can make in an hour? Well, how many pizzas she can do per minute, right? Or per hour is really going to depend on her. Assuming you two aren't like dropping pizzas and falling asleep or doing anything like that, there's always going to be a step that slows down everything else, right? There's no reason for the other two steps to be faster than that step. Of course, Michael points out we could get a bigger oven, right? That's true. You get 2 ovens, you just doubled the speed. But that kind of ruins my analogy, so I'm not talking about that. So, Paula, would you really impact the speed? Do you think it's going to take you a lot of time to take the dough out of the package and pass it off? No, so you might have 0 impact on the reaction. Do you have to have Paula in the steps, though? Without Paula, there's no pizza. No one's unwrapping the pizza. You're never getting a pizza back there to cook, right? And again, Courtney might also have 0 impact on the reaction speed because she's so much faster than the cooking step. So we're going to talk about how multi-step reactions can have weird impacts on the reaction speed. How are we going to figure out E? We're going to divide, yeah. And we're going to divide it. We're going to say, okay, remember, I'm going to probably do this one divided by that one. Or, I'm sorry, this one divided by that one. And then this divided by that. So it would be 0.75 over 0.56 to some power, because these are the molarities, they're raised to a power, is equal to the one rate divided by the other rate. What do you need to be careful of with these two rates? Yeah, they're not to the same factor of 10, are they? That was Joseph's idea. He's kind of evil. I wouldn't have done that to you, but Joseph did. So I'm going to make them both 10 to the minus 4, which moves that over a spot. So you'd have 12.8 times 10 to the minus 4th divided by 7.14 times 10 to the minus 4th. If you make them both times 10 to the minus 4th, what happens to the two 10 to the minus 4ths when you divide them? They cancel, which is why I didn't write them down. If you change them both to 10 to the minus 4th, you have 12 over 7. You simplify this math down on both sides, and you solve for n. I can't do this in my head, but that's okay because I got it all worked out right here. So here's all like the real math. So here I am doing 0.75 over 0.56. That's 1.339. Here's the ratio of the rates. That's 1.79. 1.39 does not equal 1.79, so it's not 1 to 1. So 1.339 to some power equals 1.79. Found that n equals 2. If I was your math teacher, which I am not, I would say, you got to do the log, and you could do all this fancy like non-base 10 logs. Or, what's the easiest way to solve this? It's probably the check and guess method. Let's go 1.3 to some whole number is equal to that. And try a couple of whole numbers in there. It'd probably be a lot faster than trying to work out the different log and intel. I can't do that stuff anymore, except for base 10. Other than base 10 logs, I can't do it. Do you guys even remember learning how to do that? Remember how to do it? You remember learning it, but you probably don't remember how to do it. Okay. You could relearn it if you wanted to. How would we find K for this reaction? Same way as before. Pick any trial and plug it in. So the rate is equal to C to the 1/2, D to the 0, E squared. Plug them in, you get a K value. And then you could test it just to make sure you did it right. How do I figure out the units for A? Well, not for A. How do I figure out the units for K? Let's talk about K again and the whole reaction rate. The rate is equal to K x to some n power. As n changes, the units for K will change. Rate. What are we measuring? Go away. What is changing in our rate? Now, we're not talking about meters per second. This isn't velocity. Moles per second or moles per liter second. You could write it as how is the molarity changing per second? That's usually the units for rate, molarity per second. Unless they want to write it as moles per liter. Moles per liter second. But this is the AP College Board, so they're not going to write it as a fraction. Here's how they would write it. They would write moles times liters to the -1 times seconds to the -1. Because that means the same thing, right? That means moles over liters and seconds. All right. Molarity per second is equal to K, which we're trying to figure those units out. What are the units for X if it's in these brackets? What are the brackets represent? Say again? Yeah, moles per liter or molarity. So if N is 1, then I have molarity times some K equals molarity per second. What are the units for K then? Per second, right. The units for K would therefore be 1 over second. So I'd have molarity times 1 per second equals molarity per second. What if this was squared? Well, K has to cancel out pieces to get it down to molarity per second. So it would be liters per mole second. Or 1 over molarity second. That looks like a horrible way to write that. What do you think the way they would write it? Molarity to the -1, seconds to the -1. Those are the same units as those. It's the inverse of molarity. Molarity is usually moles per liter. So they're writing it as liters per mole. So just figuring out the units for K based off of the order, you can kind of reverse it. So always got to drop it down. Yes, me. Uh-huh. Uh-oh. Let me check. All right. No issues. All right, so I think we're in the next part here. You see some natural logs magically appearing in your notes. We're on page 94 in the notes. Sounds awesome. So the way these equations are written, the first form, natural log of A minus natural log of A naught equals negative KT, that is the form that's given on the equation sheet. All right, that's the standard form. The other two are just rearrangements of that one. I prefer the second one the best though. Natural log of A is equal to negative KT natural log of A naught, because that one is a linear relationship. If you were to graph the natural log of A, that's neither an L or an N. If you were to graph the natural log of A versus T, you would get a nice line, a nice linear relationship. All right? This graph here, which is real fake data, we have not taken the natural log yet. But you see that natural occurring smooth slope that goes eventually to an asymptote where the slope is 0. That's the signature natural log relationship. If you took the natural log of this data and then plotted a graph, so here I am, here's the natural log of that data. If I plotted a graph, I got a beautiful line. Before we get into that, I just kind of got off on a sidetrack. What do all these things mean? What is A sub 0? What is that sub 0 or A naught, as it's sometimes referred to? That means the concentration at the very beginning, when the time was equal to 0. All right? That's the starting molarity of whatever your reactant is. A naught. A at time 0. K is the constant. T is time. What is the other natural log of A? That's the molarity at some future time. I really like it written like this, the second way, natural log A equals negative KT, blah, 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 all that, because it actually does line up with the y-intercept. So I've graphed this. This is the natural log of A. What is this point right here in terms of time? What would be the time right here on this graph? 0. So you plug 0 into here, that goes away, right? And y equals b, the slope. I mean, the point, what's that called? Y-intercept. And so you could write off of the graph, say here's the initial concentration. Oh yeah, that is the initial concentration from my lab. I created a solution, and that was its initial concentration. And then you have a series of times that should predict future concentrations. And it works really, really well, reasonably well, assuming the data is collected nicely. Do you guys remember your natural log laws? If you subtract 2 natural logs, that's equal to the division, right? So subtracting these 2 natural logs is the same as, it's dividing the inverse, though. It's always a weird law. It's like subtracting the 2 is equal to the second one divided by the first one. So here it is. This is the natural log law in action. Right. The negative sign went away because it got pulled over there. You're not going to use that one, but it's a pretty one also. It's just application of the natural log law. So like I just said, you could graph it, and I did. I took that real fake data, and I graphed it. I have the natural log of A versus T. I could read the point here, right? B would equal the natural log of A. Could I solve for A? I could say negative 2.3026 is equal to the natural log of A naught. Could you solve for A? How do you do that, Laura? How do you get you do the E, right? And I say you exponentiate both sides, but you just E both sides. So you go E to the negative 2.036, E to the natural log of A. What does E to the natural log of A do to that side? Gets rid of the natural log. So you just have A, because E and natural log are opposites of each other. What's the opposite of multiplication? Division. What's the opposite of anti-log? Log. What's the anti-log? It's the opposite of log. Right. It's the anti-log. So you do this, and I can't remember the answer to this, but it's a number. It's a good number. If you graphed it, could you find K? Yeah. That's a beautiful thing. Right? Guess what our next lab's going to have involved in it? Yeah. Making a graph, getting the line on there. From the line, you can extrapolate K. Yeah, it works pretty well. Yes, ma'am. Sorry, I just ma'amed you. All right, so all of this is wrong, actually. This here is wrong. I know it's not in your notes, which is good, because I made a mistake. Before we get into that, let's look at what they gave us. This is a classic, like, if you read things wrong, you'll do the problem wrong. And I typed up the wrong answer, which is kind of embarrassing. So we have radioactive element decaying, follows first order rate law, which is nice. There's other orders, second, third, fourth. We're talking about like if A was squared, that would be second order. This is a first order, so rate is equal to K x to the first power. And so if it's a first order rate law, we can use the equation we have here. The whole natural log is equal to negative KT, natural log of A naught. The first order rate constant is 0.181. What does that value represent in the equation? This is the mistake I made. So ignore all the stuff I just scratched through. The first order rate constant, that is K. That's the gigantic mistake I made I somehow made that T, and that's not going to work. So this is K. This is K, all right? We have begun with 5.28 grams. What is that in the equation? We've begun with 5.28 grams. A naught. Hey, Mr. Murphy, that's molarity, and that's grams, and that's molarity, and what the heck? I concur, Joseph. But for both of these, you'd be changing moles into mass. Strike that, reverse it. Mass into moles, which would involve the same division, because it'd be the same compound, and then dividing it by the same volume. So both of those steps would cancel out. So it's okay to leave it as just grams, because it's the same compound. And then this is the first question. This is the time. So we plug all that stuff in. We have the natural log of future A is equal to negative 0.181. There's our K. 1.96. There's our T. Plus the natural log of 5.28. I'm going to simplify that down and record what I've got so far. Negative 0.18. Oops. Helps if you press the negative sign. He's talking into the microphone right now. Plus the natural log of 5.28. So we got the natural log of A is equal to 1.309. Keeps going a bunch. Am I done? How do I solve for A? E both sides. And you get A is equal to 3.703. What are the units for A? Grams. They have to match up with the units of the original thing. This is grams of radon. So that's the mass of radon that would be left after 1.96 days. How would you do 3.82 days? The exact same. You just change the T to the next time. So that's not too difficult. Let's talk about half-life. Yeah, let's get rid of all this nasty garbage here. Oh, okay. Let me pause. So, a funny thing happened on the way to the natural log. So here's the equation. Here's the equation, right? Natural log of A minus the natural log of A naught is equal to negative KT. And it's very common with first order reactions in the rate law here to talk about the half-life of something. The half-life is a very unique point. It's where half of it has reacted or decayed, if we're talking about radioactive decay. So if Elvis has 5,000 grams of uranium in his basement, and fictitiously the half-life is 2 days, how much does he have after 2 days? He goes from 5,000 to 2,500. And then 2 days later, 1,250, half of that. And then 2 days later, 625. Let's test Michael's. And then 2 days later, all right, and then half there. Well, he's good. He's good. Okay, let's just pretend he could do that forever. You just keep taking the previous value and cutting it in half. That is actually a natural log relationship. I don't know why I'm laughing at that. But what's kind of interesting, though, is if you do the natural log of 5,000 minus the natural log, oops, that's wrong. If you did that, you do it wrong. The natural log of 2,500 minus the natural log of 5,000, you're going to get negative 0.693 is equal to negative KT. What should you probably do with the negative signs? Cancel them out. Get 0.693 is equal to KT. It doesn't matter what these two values are, as long as the initial is cut in half. It doesn't matter what they are. So if Joseph starts off with 100 grams of uranium, 2 days later he has 50, right? We could say Joseph had 150, natural log of 50 minus the natural log of 100, 0.693, because it's exactly half, and it's related to those log laws, that when you subtract 2, it's the same as taking the divisor of the 2, dividing the 2. Divisor's not a word. I'm sorry. I'm making words up here. So this ratio relationship is a given one on the equation sheet. T1 half, that means the time it takes for half of it to go away, is equal to 0.693 over K. That's just so that you don't have to go through those steps and try to work it out yourself. So we just said Elvis's and Joseph's uranium has a T1 half of what? What is your T1 half, Elvis, for uranium? You're going from 5,000 to 2,500 in how many days? I think I said 2 days. Yeah, I said 2 days. So T1 half for Elvis's fictitious relationship was 2 days. So 2 days is equal to 0.693 over K, and therefore K is equal to 0.693 over 2. And we'll have Michael divide that by 2 for us later on. But you get the idea. You could find K if you know where the half occurs. If you know the time it takes to get to half, you could find K really fast. Okay? Which is different than OK, because that is absolute zero, right? That's where a perfect crystal occurs. We are approaching, we're on like the second to last page. Yay! So we already gave a reaction example. We had Paula, Courtney, Ebony making pizza, right? Paula and Courtney are drastically faster than Ebony, but it's not her fault because it takes time to cook a pizza right. Right? The way she cooks it, it's great. It's good pizza. That's why we're not putting Paula in charge of that step. We've just given her the unwrapping the pizza part. Sorry. You guys are matchy. Like matchy. You even put boots on, too. Look at that. Twins. Yeah, same shirt. Pi Day. Okay. So, reactions in our past have occurred in multiple steps. Who here remembers doing Hess's law with Gibbs free energy or enthalpy or entropy? I know I do. There was maybe 3 reactions added together to make a 4th reaction. Pieces got canceled out. Right? Can you think of a reaction that is occurring right now in your body or in the environment that takes multiple steps? And you maybe studied some of these. Digestion, okay. That one's a little complicated. Yeah, it is. What about has anyone studied the Krebs cycle or the Calvin cycle? Calvin cycle? Yeah, Dara? That's one of those cycles in our body where mitochondria. You don't remember anymore? I'm pretty sure it's where mitochondria converts ADP into ATP, adenine diphosphate, adenine triphosphate. But point is, Junior Island. Right. You'll learn about it. You take biology in college, you'll see it again, or you'll see it for the first time. It's a multi-step cycle. Usually in AP Bio, they teach it like as a 15-step cycle, where this is converted to that, and this is converted to that, and there's like 15 steps, and it cycles back around. But some of those steps are fast, and some of those steps are slow. And so the cycle can't be any faster than the slowest step. Step 5, let's say step 5 is the slowest step. It doesn't matter how fast steps 1, 2, 3, and 4 are if there's a weight at step 5. Does that make logical sense? The same thing occurs with chemistry. Whatever the slowest step is, that's going to be our rate determining step. And the way we figure this out is just like we've been doing. We look at data and we compare it to reactions. There might be intermediates also that kind of get canceled out, which we've seen those in Hess's law. We're like, oh, we're producing, a boron, and the boron's being used, and it cancels out. The ones that get canceled out are intermediates. They're formed and used. The molecularity is the idea if you add up all the pieces, all the elementary steps, you get the big, big, big picture. All right, this first example is not in your notes, I don't believe. No, it's not. So I can just get your eyes here for a minute. So here's the entire reaction that we see on the outside, and someone has proposed that this reaction occurs in 2 steps. Because when they did the rate, when they did the reaction was not, it was not this squared, but that 2 implies this would be squared, but then they did the reaction and it wasn't squared. It was to the first order. And so they're like, well, scrap that squared stuff. Where's the first order? Well, maybe it occurs in 2 steps. And the first step, which is slow, only uses 1 N2O. Okay? And that slow step occurs, and the second that slow step is over, the second step occurs lightning fast, by comparison. Maybe this is 1 mole per 1 mole per liter second, and the other one's 40 moles per liter second. So the first one doesn't matter by comparison, and so this is the only part that really impacts the reaction, so the rate would be K N2O to the first. They would figure this out. This part here would be figured out using data like we've already been doing. Okay? Comparing, concentrations to reaction rates. And then someone has proposed how it could be broken apart. Can you find an intermediate in these 2 reactions? What's the intermediate in these reactions? I see you saying O, but are you saying O, like I don't know, or O like the oxygen? O like oxygen, yeah. It's making O and it's using O. The second step can't occur unless the first step occurs. All right? And once the first step occurs, yeah, I just recorded the snap. Once the first step occurs, the second step occurs much faster. So this is the reverse. And, Ebony pulls the pizza out of the oven and she hands it to Michael. Box! Immediately boxed, right? But you can't box the pizza until she pulls it out. So it's an immediate follow-up step. By comparison, in reality, it would take you time to fold the box. But that time would be nothing compared to her cooking it to perfection. So here's another example of the same idea. This is also not in your notes. I'm going to skip to the ones that are in your notes. Feel free to come back and take a look at this example. Here's the one that's in your notes. We have 2NO plus 2H2 producing 2 waters and nitrogen. Experimentally, they determined that as the rate, meaning they had data like we've already been doing in the chapter, and they got the rate is equal to K NO squared H to the first. That doesn't match perfectly with the equation, though, does it? Looking at this equation, you would have thought squared, but only one of the hydrogens seems to matter. So they proposed a couple of options. Option 1, option 2, and option 3. One of these 3 reactions has to be slower than the other. All right? So let's say for a second that Michaela, Mark, and George are carrying a canoe to the Potomac River. Which of these is by 3 people is the slowest in carrying the canoe? They both said George. I would have said Mark. But okay. So George is the slowest of the 3. Can you go faster than George? Not if he has to be carrying the canoe because it's too heavy for you and Mark by yourself. No. You can't drag him along. You're going to fall. You're going to take a canoe to the head. That's a bad day. So the slowest step, does it matter if George is in the front, the middle, or the last? Not really, no. But in the other scenario, Ebony is the slow step cooking the pizza. You 2 occur immediately. But without you 2, the pizza doesn't get cooked. So you two have to be factored in. We just end up adding the three of you together. So let's look at the first scenario. And this is something you're going to have to do. This is something you're going to have to do right here. I will give you multiple reactions. They add together to make this reaction. And then Dara is going to have to say, is it slow, fast, fast? Is it fast, slow, slow? Or is it fast, fast, slow? The reactions are in the same order. We're just trying to figure out who's the slowest step. So the first one's easy. If this is the slow step, then the only things that would matter are those two reactants. Once those two reactants react, the whole rest just occurs almost immediately. So it would have been NO to the first, H to the first, because those are the only two reactants in there. Does that match with what the data told us? That does not match. So it can't be slow, fast, fast. Let's try the second scenario. In the second scenario, NO and H2 react, then the second slow step could occur. Now, you can kind of do algebra with this, which really throws some people off. If you have an intermediate, and nitrogen is the intermediate, you can substitute it out and replace it with the other pieces. Water is weird. What do we deal with equilibriums in waters? How do we deal with water when we're dealing with equilibrium? Replace it with a 1. So we're allowed to kind of ignore the water because mathematically it has very little impact on everything. So these two can be substituted in for that N. And when you do that, you have NO plus H2 plus NO produces N2O for this slow step. How many NOs are there? 2, which matches up with our squared. How many H's are there? H2s? Only 1. So that matches up with this proposed, this rate that was determined by the data. All right? We could substitute the first reaction, if it's faster, into the second reaction if it's slower. What if the third reaction is slower? Substitute the second into the third, and then the first into the second. And so the third includes everything, which it did not. So this is kind of weird. I think I could tell by Manjot's face that he thinks it's weird. Right? The last piece we're going to have to do next class. It's not hard, but we're just out of time. So.